A current-carrying conductor placed in a uniform magnetic field experiences some force. The magnitude of this force is determined by using the formula F is equal to BIL sin theta, where theta is the angle between the direction of the magnetic field and the direction of current. The direction of the force acting on the conductor can be determined by using Fleming's left-hand rule. According to the rule, when we stretch the thumb, the index finger and the middle finger on the left hand in three mutually perpendicular directions, if the middle finger indicates the direction of current in the conductor, the index finger indicates the direction of the uniform external magnetic field. Then, the thumb indicates the direction of the force on the conductor. Now, let us discuss the forces acting on a rectangular current-carrying loop when it is placed in a uniform magnetic field. Consider a rectangular loop PQRS of length L and breadth B placed in a uniform magnetic field in such a way that the plane of the loop is parallel to the magnetic field. Connect the rectangular loop to a battery as shown, such that the current in the loop is along the direction PQRS. Let B be the magnetic induction of the uniform magnetic field between the two magnets, and I be the constant current passing through the rectangular loop. To simplify the understanding of the topic, we neglect the ends of the loop from where the current enters and leaves the loop. The magnetic field exerts some force on the arms of the current-carrying rectangular loop. The direction of current in the arm PQ of the loop is perpendicular to the direction of magnetic field. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1 is equal to BIL sin 90, which is equal to BIL, where L is the length of the arm PQ. Let this be equation 1. Here, the direction of the force is determined by using Fleming's left-hand rule. Stretch the three fingers of left hand in three mutually perpendicular directions. Here, the direction of the magnetic field is from north to south, represented by the index finger of the left hand. The direction of current is from P to Q of the rectangular loop, represented by middle finger, and the direction of thumb represents the direction of force acting on the arm PQ of the loop. That is, the force is acting downward with respect to the plane of the loop. The direction of the current in the arm QR is parallel to the direction of the external magnetic field. This implies that the angle between the direction of the current in QR and the direction of the magnetic field is 0 degrees. Sin 0 is equal to 0. Hence, the magnitude of the force acting on the arm QR of the rectangular loop due to the magnetic induction B is F2 is equal to 0. Let this be equation 2. The angle between the direction of the current in RS part of the loop and the direction of the magnetic field is 90 degrees. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3 is equal to BIL. Let this be equation 3. Here, using Fleming's left-hand rule, we find that the force acts upwards with respect to the plane of the loop. The angle between the direction of current passing through the arm SP of the loop and the direction of the magnetic field is 180 degrees. Sin 180 degrees is equal to 0. Hence, the magnitude of the force acting on the arm SP of the rectangular loop due to the magnetic induction B is F4 is equal to 0. Let this be equation 4. We observe from the equations that the magnitudes of F1 and F3 are equal. As they act on the loop in opposite directions, they are unlike forces. Hence, the net force acting on the body is 0. As the two forces F1 and F3 are non-collinear and are separated by the perpendicular distance b, which is equal to the breadth of the rectangular loop, they result in turning the loop. These two forces cause the rectangular loop to rotate about an axis that lies in the plane of the loop, parallel to its length and passing through its center. Thus, the axis of rotation of the loop passes through the midpoints of QR and SP. The magnitude of the torque τ1 due to F1 is equal to the product of F1 and the perpendicular distance between the point of application of F1 and the axis of rotation. This gives τ1 is equal to F1 into half of B. Similarly, the magnitude of torque τ3 due to F3 is equal to F3 into half of B. The net torque on the loop τ is equal to the sum of τ1 and τ3, which is equal to F1 into B by 2 plus F3 into B by 2. But F1 is equal to F3 and both are equal to BIL. Then τ is equal to BIL into B by 2 plus BIL into B by 2, which is equal to BI into LB. As L into B is equal to the area of the rectangular loop A, we can denote the torque acting on the rectangular current loop τ is equal to BIA. The net torque on the loop tends to rotate it in the anti-clockwise direction when viewed from SP side of the loop.